Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video where we look at exact values in trigonometry and then the unit circle. So firstly, to exact values. So normally if you put things on your calculator like sine 20 or cos 40, tan 50, you get this weird number. It's irrational. Decimal goes on forever. You can't write it exactly. It turns out though there are a few values of theta for which we can write exact values of sine theta, cos theta, and tan theta. So let's have a look at these. So we're going to fill out this table and we're going to also look at why the value of sine theta, cos theta, tan theta is as it is. So let's look at this right angled triangle here. Here's the right angle. So let's say this angle here is 45 degrees. Well, that means, of course, that the other angle here must be 45 degrees because the three angles need to add up to 180. So, of course, that means that this is an isosceles right-angled triangle. So two sides will be equal. Of course, they're the two shorter sides. So let's say I call this side here A. Then, of course, the other shorter side will be A. Now, the longer side will be, using Pythagoras, the square root of shorter side squared plus shorter side squared, which of course is the square root of a squared plus a squared is 2a squared. And using your knowledge of surds, that's just the square root of 2 times the square root of a squared, or the square root of 2 times a. So what I've just proved to you using Pythagoras is that if you have a right-angled isosceles triangle, then the hypotenuse is always root 2, which is about 1.4, times each of the shorter sides. So I'm just going to rub out that working out. Please pause and copy it down if you need. So we have that the hypotenuse is root 2a. So if we look at this 45 degree angle, it wouldn't matter which of the 45 degree angles I used, but of course I have cos of 45 equals adjacent over hypotenuse. So it's a over root 2 times a, and of course the a's cancel out. I'm left with 1 on root 2. So I can fill this in my table. Cos of 45 is 1 over root 2. But that would be exactly the same for sine 45. Sine of this angle is a over root 2a, which is also 1 over root 2. But what if I took tan of this angle 45? So tan of this angle here is opposite over adjacent. It's a over a, which is 1. So, now look at a right-angled triangle with a 30-degree angle and a 60-degree angle. It turns out if you have a right-angled triangle like this, where we have the 60-degree angle double the 30-degree angle, it turns out that the longer side is double the shorter side. So if I call this shorter side here B, then the longer side, which in a right-angled triangle is the hypotenuse, is 2b. So what would this third side be? Again, I can figure it out using Pythagoras. It's the square root of longer side squared minus shorter side squared. So 2b all squared is 4b squared. 4b squared minus b squared is 3b squared. Once again, as the trick I used in the previous example, I can write this as the square root of 3 times by b. Once again, I'm going to rub out this working out in red. Please pause and copy down if you need it. So this shorter side we found out was root 3 times b. So let's go and calculate the ratios. So let's look at this angle first, the 30-degree angle. So sine of 30 is opposite over hypotenuse. So it is equal to a half. Similarly, cos 30 will be adjacent over hypotenuse. Once again, b's cancel out as they did up there, and I'm left with root 3 on 2, which is about 0.866 and so on. Tan of 30 will be opposite over adjacent. Once again, can cancel out the b's, and I'm left with 1 over root 3. So I can now fill in this row of my table above. So when I've done that, I can also look at this 60-degree angle here, and I can do the same thing. And you should get sort of the opposite sine and cos switch around. So sine 30 was a half, cos 60 is a half. Cos 30 was root 3 on 2, sine 60 is root 3 on 2. Tan of 60 will be root 3b divided by b, which is just root 3. Alright, I'm going to get rid of these two triangles and the working out now. Please pause and copy down if you need it. So let's now look at the case of 0 and 90. So this is probably a little more challenging to understand. Of course, we're not really using trigonometry in a right-angled triangle where we have a 0-degree angle. That doesn't really make any sense. But what we're going to do is we're going to draw a right-angled triangle where the angle is very close to 0. So let's say we have a right-angled triangle like this, and we call this angle theta. So you can see theta is very, very small, so sort of close to 0. So what happens is as theta, this angle gets closer and closer to 0, what you can notice is that this side here, the adjacent, is very long compared to the opposite. In fact, the adjacent is almost the same length as the hypotenuse. And it turns out that if I were to make theta even smaller, so let's draw another triangle where theta is even smaller, like this, then the hypotenuse and the adjacent would be even closer and closer together in length. So what's happening is as theta, this angle, gets closer and closer to 0, the adjacent is almost the same length as hypotenuse. The adjacent approaches the length of the hypotenuse. And if the adjacent and hypotenuse are equal, then cos theta would equal 1. Adjacent over hypotenuse would be 1. But you can see that what's happening is that the opposite is getting very, very small. It's getting smaller and smaller as theta gets closer and closer to 0. So sine theta will get closer and closer to 0. This, of course, means because the opposite is getting very small and tan theta is opposite over adjacent, so if we just look at that, tan theta opposite over adjacent, if this one gets very, very small and this one's getting very, very large, it's going to get closer and closer to 0 as well. Because if the top number gets closer and closer to 0, so does the whole fraction. It switches around for 90 degrees. So let's say, instead of calling that angle theta, I'm going to rub this out and call the other angle theta. So if this angle here is close to 0, this one here is getting closer and closer to 90. Of course, as you know, if we switch around the angle as we have done there, then the opposite and adjacent switch around. So this side here becomes the adjacent and this side becomes the opposite. So the opposite of what happened before is now happening. The adjacent is getting very, very small compared to the hypotenuse. So as theta gets closer and closer to 90 degrees, cos theta gets closer to 0. Sine theta gets closer to 1 because the opposite and the hypotenuse are getting very close together. And then if we look at tan, well, tan is still opposite over adjacent. That part hasn't changed. But what's happening is this number here, the opposite is getting very large and the adjacent is getting very small. When you have a large number divided by a small number, you get an even larger number. So tan theta actually just gets larger and larger. It approaches infinity. So hopefully you can see a trend here. Sine theta, as we go down, is increasing. It's going up, up again, up again, up again. Cos is doing the opposite. It's actually going down each time. It starts at 1, then it goes to about 0.866, then about 0.707, 0.5, and goes down all the way to 0. Tan, like sine, is getting larger and larger each time, okay? So that's all for the exact values part, but what about the unit circle? What's this got to do with anything? Well, we are actually going to learn how to use trigonometry in non-right-angled triangles, and sometimes you will have an obtuse angle. We want to be able to sort of understand what would be sine theta, cos theta, and tan theta when we take angles that are more than 90 degrees, so that are down here. So let's say, for example, I wanted to find the sine of 150, the cos of 150, and the tan of 150. Okay, we're going to need to be able to do that to find unknown sides and lengths in non-right-angled triangles. So now we're going to look at the unit circle, which tells us how we can figure out the values of these. It turns out we're going to use this table here. So please pause and copy down the table or anything if you need, because we're going to go on to a new slide. So we draw a unit circle in the Cartesian plane. Unit circle means the radius is 1. So those two numbers will be 1. Because we're in the Cartesian plane, this will be -1 and -1. So we've got our normal x and y axis. So let's draw a right-angled triangle like this. So the radius is 1, so this length here would be 1. So this length here is just whatever the x-coordinate is, and this length here is just whatever the y-coordinate is. So if we call this angle theta, so theta will be the angle made with the positive x-axis, we can find the three ratios in terms of x and y. So if we start with sine theta, it is just opposite, which is y, over 1. So the sine theta is the y-coordinate. Cos theta, similarly, is the adjacent, which is x, over hypotenuse, this hypotenuse there, which is 1. So cos theta is the x-coordinate. Tan theta is the opposite, which is y, over the adjacent, which is x. So if you like, it's actually equal to sine theta over cos theta. Okay, so that's how we're going to use this unit circle. Cos theta is whatever the x-coordinate is, sine theta, whatever the y-coordinate is, and tan theta is the y-coordinate divided by the x-coordinate. So it turns out from our previous slide, we know that if I make this angle here into a 30-degree angle, let's say theta was 30 degrees. Well, we know that sine theta, sine 30, is equal to a half, and we know cos 30 is equal to root 3 on 2, which is about 0.866. So this point on the circle will be x-coordinate cos, y-coordinate, which is sine. So I wanted to find out what is, say, sine and cos of 150, and then I'll be able to find what tan of 150 is as well. So what we do is we always, when we're using this unit circle, we consider the angle, in this case 150, to be the angle made with the positive x-axis, and we're going in an anti-clockwise direction. So the 150-degree angle, we start here and we go this way 150 degrees. So let's draw another right-angled triangle. Have our right-angled triangle, and once again the hypotenuse would be 1 because the black circle is a unit circle. It has radius 1. So if this angle here, from here to here, is 150, then this angle inside the triangle would be 30 degrees, right? So it would be the same as the triangle I drew originally. They would actually be congruent triangles. So I figured out that this distance here was a half. We knew that. So the distance here will be a half. So that means for this point, the y-coordinate would be a half. Now this distance here would be the same as this distance here, which would be root 3 on 2. But the x-coordinate over here is negative. So this point here would be negative root 3 on 2. So how do we figure out sine 150 and cos 150? So sine 150 is the y-coordinate, so it's a half again, and cos 150 is the x-coordinate. So it's the same as before, except this time is negative. So then, of course, if I wanted to find tan of 150, it's the y-coordinate divided by the x-coordinate. So it's a positive divided by a negative. It will also be negative. It'll be -1 on root 3. And that's how I figure out the sine, cos, and tan of angles that are more than 90 degrees. They will have a corresponding angle in the first quadrant between 0 and 90 degrees. So I just find that corresponding angle and decide whether it's positive or negative. Now in the first quadrant, this quadrant here, x and y are always positive. So sine, cos, and tan will all be positive. That's what the A means, all. Now over here in the second quadrant, you can see that the y coordinate is positive, the x coordinate is negative. So as we saw here, sine is positive, but cos and tan are negative. So only sine is positive. That's what the S means. Now if I go to the third quadrant, you can see the y coordinate here is always going to be negative. So sine's negative. Cos is also negative, which would mean tan, a negative divided by a negative, is positive. So only tan's positive in this quadrant, and in the fourth quadrant, only cos is positive. So you might remember it as all students take calculus, or you can substitute the words, make up your own mnemonic device, or whatever. All are positive in the first quadrant, only sine in the second quadrant, only tan in the third quadrant, and only cos in the fourth quadrant. Okay, so let's figure out how we might find angles of other magnitudes. So let's say that I wanted to find cos 240, okay? So I'm going to draw up the Cartesian plane again. You don't always have to do this. Hopefully you'll get good enough that you don't need to draw it. So remember, x-axis and y-axis, I'm always looking at the angle made with the positive x-axis anti-clockwise. So 240, I go 90 to here, 180, and then I need another 60 to go here. So this angle here will be 60 degrees. So what I can do is think that this will be the same magnitude as a triangle in the first quadrant with angle 60 degrees. So draw one like that, and then this angle here will be 60 degrees. Now I know from my table cos of 60 was equal to 1/2. So if I were to draw a unit circle around these two triangles, I know that I would have this distance is equal to 1/2. So this distance must be equal to 1/2. But because I'm in the third quadrant, remember it goes all students take calculus, only tan is positive in this quadrant. Cos is negative. So cos 240 will have the same value, 1/2. The only difference is it will be negative. And we can work this even for angles that were not on our original table. So for example, you saw there wasn't like 34 degrees. It wasn't on our original table. So let's say I wanted to find tan of 326 degrees. So tan 326, if I go all the way out to 326, that angle there will be 34 degrees. So tan 326 is the same as tan of 34, except in the fourth quadrant, tan is negative. So tan 34, if you put on your calculator, is 0.67, so tan of 326 is minus 0.67. So what would be something like sine of 180? Well, we know sine 0, remember, was 0. Because at 0 degrees, the y coordinate along here is 0. So at 180 degrees, which is over here, sine will be the same, have the same y coordinate of 0. Alright, I know that this is some tricky stuff. Please make sure you ask questions if you need. This has been the luckiest maths teacher in the world. Have a great day.